The name of this video is Maxwell B local case 2 Ampere. In the previous video, we investigated the solenoidal property of B in presence of a Js, that is a current density on a surface. Now we want to investigate Ampere's law. As it turns out, this case is pretty complicated, so I will not make a full demonstration here, which is in the notes. The notation becomes really wide, so I will not do it here. But I just want you to grasp the main concept behind this, which is quite important, particularly later on in 3,4D2. So, if we use the same notation as in case 2 solenoidal, for example, we consider the same point capital P on the surface capital sigma where there is a Js vector there. Using the same notation, the way people write down this case is as follows. N, the same n which goes from 2 to 1, I remind you, so it's n cross a quantity in bracket like this, B in bracket, and I will tell you in a few minutes what this means, equal mu naught times vector Js, which again is only on a surface in this case, it's not in a volume, so it's a discontinuous in a volume sense, in a three-dimensional sense, a current density vector. Alright, so to understand this, which again is quite complicated, let's focus one more time to exactly the same point, capital P, we considered in the previous case. So I remind you that in the case of case 2 solenoidal, we had a cylinder, and I kind of sketched in these directions. There was the z-axis of the so-called local Cartesian coordinate system. In that example, I only sketched the z-axis. Here we are going to sketch the whole x, y, z local Cartesian coordinate system. So I tilted it like this. Now, for simplicity, if you look at that video, let's tilt it up z in this direction. It's just simpler. So, if we do so, the xy plane will be tangent at capital sigma, see the previous video, at point capital P. And let me sketch it in this fashion, for example. This is the x-axis. Normal to it, of course, there will be a y-axis here. This is my point capital P, which is also the origin of this local. This is called a local coordinate system, CS for coordinate system, Cartesian in this case, obviously. Z, again, I tilted it, so it goes in this direction. And it's a three-dimensional representation, of course, of this problem. This is Z, and this is my point capital P, okay? So the xy plane, again, is tangent at point capital P to capital sigma. So in this case, the vector Js will also be tangent. So we'll have 2 or 3 Cartesian coordinates. Well, if it is tangent, for example, we can sketch it in this way here. If this is my Js vector, clearly it will have only two components, x and y, because it's tangent, so it has to reside on this plane, which is the tangent plane to capital sigma. So there will only be a component, a Js vector along x, and similarly here, there will be a component, J vector. I will put it later because there will be more things, so I don't want to overload the picture yet. This will be the y component, of course, of Js. Good. So now the normal unit vector upon capital P points in this direction. It's n, and again, I don't specify this n here. That goes from 2 to 1. Okay, it's the same sketch as before, and again, let me write this right away so we don't forget. This point here is exactly the same point, capital P, we considered before. Okay, I didn't sketch capital sigma for simplicity. All right, so now we have a local Cartesian coordinate system in this fashion. We have n, which points to from 2 to 1, so in the same direction as z, so it's basically uz if you want, and I will come back to that in a minute. So now we want to use Ampere's law. Okay, so Ampere's law in local form, we cannot use it because the kernel is not well defined in this case, but the integral form is always well defined. So we can definitely use it also in this specific case. And so, for example, let's consider a closed line which I call a cut line type. And so this cut line type is something which goes in this direction, so it's parallel, it goes from point A, let's say here, parallel to the x-axis until a point B, so this is point A, it goes in this direction from point to point B, then this cut line goes down here it becomes invisible because it goes on the other side, and similarly here it becomes invisible because on the other side, and here is invisible on the other side, parallel again to the x-axis. So this will be B, this is for example C, and this one is point D. I will only sketch two of them, not to overload again the figure. And I go in this direction, so this is my right hand rule, okay? So the right hand rule goes in the same direction as Y in this case. Good. All right. So with this is this line is my cut type line, which I need to use, so gamma cut, okay, which I need to use in the Ampere's law. As a matter of fact, I will tell you this in a minute, you need two of these cut lines because there are two components of JS in this coordinate system. So this one will be the first one. And I will let you discuss in Piazza how to do the same demonstration for the other component of JS. So now I will not even do the demonstration. I will just try to give you a concept of how this works only for this specific cut type line. But you need two, because again, there are two components, JS X and Y. So this complicates things a lot. But this is a beautiful, compact, and elegant version of this Ampere's law in this case. So let's investigate it. It's very important, in fact. All right. So now that we have all that, for example, we will know that we want, as always, we want the height of this structure here. This is h. And as always, eventually we want h to go to 0 plus, so that we squeeze down this cut line around point capital P so that we investigate B around that point P. And any contribution of the circulation along these two segments does not contribute the finite circulation in this limit as before, as always. All right. Whereas the other direction here, it's a finite but very small quantity, a physics infinitesimal, really, if you want, a delta x. This is our physics infinitesimal, okay? Great, so now we have our physics infinitesimal, so this is this quantity, so these two lines will contribute to the circulation of what? Of the B field, which somewhere here, for example, can be this is B1, we don't know anything about it, we want to find the generic property of it, and this, for example, will be B2, region 1, region 2, exactly as before. Of course, these B components can have three coordinates, x, y, z, whereas J can only have two, x and y, because it resides, it has to be tangent, of course, J, so it has to be only two. Now, with all of this nomenclature at hand, we can start to specify one by one what these quantities are. So, for example, n in this Cartesian coordinate system, it's nothing but 0, 0, 1, because effectively is nothing but uz, if you want. But let's write it in this fashion. So similarly, what about B1 vector? Well, B1 vector will be B1x, B1y, and B1z. And similarly, of course, for B2, I'm not going to do that. Same thing. Just exchange 1 with 2. What about the strange symbol bracket? That's what people use to identify difference between two coordinates. So this means that bracket B vector is the difference component by component. So it's B1x minus B2x. So it's the discontinuity, if you want, in proximity of capital P, B1y minus B2y, and finally, B1z minus B2z. Now, let me ask you this, and this you discussed in Piazza. Do we already know something about this component here? Is it continuous or discontinuous? Discuss this in Piazza. Great. So now we know what this bracket means. And finally, we need to identify mu naught, of course, is a constant. What about Js? Well, Js, obviously, it's a vector with two components. So in this case, as the component Js along x and Js along y. Since now we have almost everything here, I can put it here. This is Js along y. And there is not the component, because it's tangent to capital sigma upon capital P. So these are all the vectors included here. So now we know how to compute with the vectors this vector product, okay, in this vector form. And so we know that n vector b, actually, we can write it very simply as the determinant, and then we use Sarro's rule to solve it quickly, of so let's begin. The last entry is this complicated one. So let me rewrite it for simplicity, for one time, so we don't make a confusion. So it's b1x minus b2x. Then it's b1y minus b2y. And finally is b1z minus b2z. And this, up here we have ux, uy, and uz. And here with n, and n is 0, 0, 1, as we can see there. All right, so this determinant can be readily calculated. For example, this gives me 0 when I do this product with Sarro's rule. This gives me 0. This one doesn't give me 0, so the first component I have is, interestingly enough, and this complicates the notation a lot, unfortunately, b1y minus b2y times 1 times ux. So the y component different gets multiplied by x. And then similarly, this is 0, and this one, the y components, the similar thing. So the first one was the x components, and the next one is going to be so this, we have done it with x. So now we do this, and we do the y components, but with a minus sign. So we have a minus b1x minus b2x times uy. And let me confirm that I'm not doing this wrong. So the y gets a minus sign. I've done it exactly the other way around. So typical mistake. So this gets a plus, and this one with the y component gets a minus. So I've done it the other way around. So that's why it's good to check. So you do this simple calculation here, and that's what you get from this determinant. And this has to be equal. This has to be equal to mu naught times j, but this has only two components, which are the two components in fact we have here, interesting of course. So it's mu naught times js x ux plus js y uy. Okay, so for example, we could investigate only, let's say, the let's investigate, for example, the x component here, with the one with the positive sign. So this quantity has to be the same as this quantity here. And so from this, eventually, I get b1x minus b2x. ux, or uy, of course, goes, of course, in this case, this is the y, so I need to pick this component here, not this component here. So let's erase that. As you can see, it is fairly complicated, this whole thing, and it's very easy to get entangled with what is x and what is y. That's why I don't do the full proof. I used to do it in the past. This is really complicated, and it becomes very wide very quickly. So this one is simply mu naught jx, this is x, plus this one is y. Clearly, this is the y. So here I need to pick up the y component. So it's b1x, and uy will just get rid of it. And so this one gives me equal to mu naught. I need to keep, of course, still mu naught, obviously, times jsy. This is quite interesting. the x components of the B field in this local Cartesian coordinate system show a discontinuity of the first kind with respect to the y components of JS. Doesn't get more complicated than that. Now let's try to understand this a little bit. So now this notation should be somewhat clear at this point, given all that. And so if it is clear, what we can do next, we can try to attach a little bit some more physical sense to this point here. What is actually that we are trying to use? We are trying to use Ampere's law. I didn't even write it down and not to overload this board. But the way it works is that here we have a line which is linked with the current, and we'll do the right-hand rule, which goes in this direction. And so if you note that, you will see that now what you need to do, the critical thing here is that in 3D, the definition of current intensity is the flux through an open surface, capital sigma, whatever that is, of J dot NdA. What about in 1D, which is actually what's happening here? So we are doing a flux in 1D. This is the flux of J in 2D to get I. But if I want to get IS, which is the current intensity on the surface associated with JS, I need to do the flux, and it's not a line integral, it's a flux. It's a flux over line gamma, which, for example, in this case, could be the trace of gamma cut 1, let's call it gamma 1, in fact, along the x-axis, so let's say gamma 1, to be complete, of what? Of JS dot, in this case, in general, it would be JS dot TDL. Okay, so in general, let's do it before going to gamma 1. Let's keep it general for a second. So we do gamma, and this is J dot TDL. And in the specific case of this line here, this would be IS, let's give it a name, is in the y direction. Okay, it's associated with this quantity here if you want. So this ISY, of course, IS is not a vector, but I can still do the flux. When I do the flux, I only get one effective scalar, okay? So just be careful with that. So I just define it with this name. It's not part of a vector, of course, a scalar. And I do the line integral on gamma 1 of JS, what JS? Only JS y, the y component of JS. In this case, T is UY, is the normal unit vector at this line, which is effectively my one-dimensional surface, if you want. I know this is pretty complicated, times the length of the line, which is delta x. All right, so that's what you get. So this is the final result. Since this line is only delta x long and this is a physics infinitesimal, effectively this integral boils down to this result here with the plus sign, because with the right-hand rule, this current is crossing the same direction as the orientation of this line ABCD, if you remember Ampere's law and the concept of linkage. So that's why you get a plus sign, okay, in this case, and you get this final result, which is just a subset of this very compact version up here. All right, so now, if you want to show the other case, so minus B1y minus B2y equal mu naught JSX, so the x components, where y, the discontinuity of y goes with x, you need to choose another line, and I will let you think about this case here. In Piazza, what kind of line, gamma cut 2, would you use in order to show this, to give me a similar kind of concept with the 1D flux concept, which is really key here, for this other component of this Ampere's law case 2. So I really wanted to discuss this in Piazza. The last thing I would like to discuss in Piazza is what happens if I choose, what if I choose the convention that n, instead of being from 2 to 1, is from 1 to 2. And that's quite relevant for 342, because as it turns out, later on when we do magnetization, typically people don't write n vector p, but write b vector n, or m vector n, for conventions, okay? So you need to just keep this in mind. You need to think about that, and I want you to discuss about this in Piazza. All right, so to summarize this video, here I wanted to give you a sort of general concept of something quite complicated, which is, and so don't be worried if you don't fully understand this. It is complicated. Maxwell B local case 2 Ampere, and so in this case we use the same notation as case 2 solenoidal. This equation reads n vector b equal mu naught j, but this in brackets, which means this bracket is just representing discontinuities, the difference between the x, y, and z components with respect to this local Cartesian coordinate system of the B fields, just above and just below the surface capital sigma, which contains this point capital P. And we define a local Cartesian coordinate system is 0, 0, 1, and so J has to be tangent, that's why there is not 0 here. So we can write this determinant to write this equation here in a Cartesian coordinate system, of course. We get this result where the discontinuity of y goes with x, and the discontinuity of x goes with y, minus sign, think about the right-hand rule, and I want you to think about that. And the key concept is the concept of one-dimensional flux versus a two-dimensional flux. And I know that people here have lots of difficulties to understand that. You need to meditate about these equations down here to fully grasp this concept. So with this, we complete our study of the local case 2, which is in presence of currents on a surface. And that's it.